Today's lecture covers what is called the Lorentz Transformation. The Lorentz Transformation is the special relativity equivalent of the old-style Galilean transformation from the first semester. It's a portion of the theory of special relativity. Now consider conceptually the following example. Let's say that we have two starships that are moving away from the Earth in opposite directions. Let's say that one starship is moving in that direction relative to the Earth at 90% the speed of light. Let's say the second starship is moving in that direction relative to the Earth at 80% the speed of light. If you use old-style Galilean relativity to describe the speed of one starship with respect to the other, you would end up with something greater than the speed of light, 1.7 times the speed of light. We already know from time dilation and length contraction that that cannot happen. So then therefore, how do we account for this? In other words, once again, what is the special relativity equivalent of the old-style Galilean transformation? This is what is called the Lorentz transformation. And when I derive the expressions for the Lorentz transformation, we're only going to consider one-dimensional cases. We did two-dimensional cases back in the first semester for Galilean relativity. It's not necessary for our case here. One-dimensional cases is good enough. Okay, so this is what is called the Lorentz transformation. This is the special relativity equivalent of the Galilean transformation from the first semester. Okay, as I said a moment ago, we're only going to look at a one-dimensional case, and that's going to be the case in the x direction. So we'll consider a one-dimensional case only. Okay, so here's then how we're going to go about setting this up. Let's say that I have two reference frames, a stationary reference frame O and a moving reference frame O prime. By definition, the moving reference frame will be moving in the positive x direction with a velocity u. So u is going to be the velocity of O prime with respect to O, just like it was, for example, back in the first semester for the Galilean transformation. Once again, however, we're only going to consider motion in the positive x direction. Okay, now according to O, we're going to draw up the situation in the following way. So let's say at times t is equal to 0, I have my two reference frames here, O and O prime, lined up together. Here's how I demonstrated this back in the first semester when talking about the Galilean transformation. If you recall, we thought of yourselves here sitting in the classroom as the stationary reference frame, and I was the moving reference frame. And then we considered the door of the classroom to be the origin, and at times t is equal to 0, I was lined up with the door. Okay, and then let's say that some time goes by. According to O, we're going to label the time that goes by as capital T. And then right here in the room is me, the moving reference frame O prime. And then we have an object somewhere in the room. If you recall in the first semester when I demonstrated this, the object was a student walking through the room. So let's say that right here, for example, is the object. And now I'm going to draw up my vectors here, my position vectors, but when I do, I'm only going to worry about the positive x direction. Back in the first semester, we did the two-dimensional case, we included the y direction as well. Not so here, just in the x direction is perfectly fine. Okay, now, according to the stationary reference frame O, the object here in the x direction has a position. That position I'm just going to draw like so. This position here is referred to as x. Okay, now think of yourselves as the stationary reference frame O and consider x to be a meter stick. So that meter stick, for example, x is stationary with respect to you. I'm going to set it here on my desk to illustrate. Okay, and then we have the position of me relative to you guys here in the room, once again in the x direction. That's this vector right here in the diagram. This right here is just ut. Okay, now back with the old-style Galilean transformation, we then labeled the position of the object relative to me right here on the diagram like so as x prime. And then when we added up the vectors very simply, it was ut plus x prime is equal to x. And now we're going to take relativistic effects into account. Specifically, in a few minutes, we're going to take length contraction into account. So because of that, I'm not going to label this as x prime. Instead, I'm going to label it simply as s. However, on my diagram, I'll now just add everything together. We have here ut plus s is equal to x. Like so. Okay, once again, in the Olsztyn-Galilean transformation, this right here was x prime, and then therefore we simply had r was equal to r prime plus ut. That was the first of our Galilean transformations back in the first semester. Okay, now here's what we didn't do in the first semester. What I didn't do was I did not redraw out this diagram, but according to L prime. Now I'm going to do so here because we're going to take into account relativistic effects. So then therefore this is what the situation looks like according to me, according to O prime. Okay, so once again at times t is equal to 0, the two reference frames O and O prime are lined up. Okay, now because I am moving relative to you guys, this then means that we measure different amounts of time for this scenario. So up on the top board, you guys measured the time interval, for example, as capital T. Here on the bottom board, according to me, O prime, I'm going to measure this now as a capital T prime. So let's say that a capital T prime amount of time goes by. Like so. And then here I am. Okay, and then we have our object. Like so. And now according to me, that object now has a position. That's this vector right here on the diagram, and this right here is x prime. Think of x prime as another meter stick, but it's a meter stick that is stationary with respect to me. That is, it's in the same reference frame as I am, O prime. Once again, I'll take this stick and place it here to illustrate like so. Okay, now according to me, I have a position here relative to the origin, relative to the door here in the room. Up on the top diagram, remember that that was referred to as x. Here on the bottom diagram, however, because we are going to take into account length contraction in just a few minutes, this is referred to as capital R. Okay, and then lastly on this diagram is this vector right here. This is the position of me relative to you guys, but as seen by me. This is the ut vector once again, but this right here is labeled as ut prime. And now let's just add everything together here on the board. Notice that ut prime plus x prime is equal to r. Like so. These two equations here and here are identical to each other in the old style Galilean relativity. But as I said, now we're going to go ahead and take into account length contraction. So for example, here on the bottom board, I have this meter stick x prime. X prime, for example, is stationary relative to me. However, on the top board, you guys see the x prime as s, but that meter stick is moving relative to you. So then therefore, s is the length contraction of x prime. So up here on the top board now, let me label it as such. S is the length contraction of x prime. So notice that I'm using here the length contraction equation from last time in class. Once again, to illustrate, think of it like this. Here on the bottom board, I've got a meter stick with me. That's x prime. It's stationary relative to me. However, on the top board, you guys see that meter stick as moving. You guys see s. So then therefore, s is the length contraction of x prime. Okay, and now to get the first of the Lorentz transformation equations, now what I do is I just substitute into this expression here for s this quantity here. Like so. This guy right here is the special relativity equivalent of the old Galilean transformation of r equals r prime plus ut. Notice how this expression works. For example, if u is small, as it is in the classical world, the speeds of ordinary objects around us is very small compared to the speed of light. If u is very small, then this term here is essentially just equal to 1. And then therefore you have r equals r prime plus ut. So the old-style Galilean transformation is an approximation of what really happens. What really happens is this expression here. Okay, usually this expression here is written in terms of x prime. So I'm going to go ahead and write that on the far board. I'm going to subtract the ut here to the other side and then divide by the square root. Like so. Okay. And then this right here is the first of the old-style Galilean transformation equations, now rewritten in its special relativity equivalent. Okay, now, this expression here. Let's say that up on the top board, you guys have that meter stick. That was this one here originally. Your guys' meter stick, that's x. It is stationary relative to you. However, according to me, because I am moving relative to you, I see your meter stick as r. However, I see it as being length contracted. So then therefore, r is the contraction of x. That's this expression here. So once again, on the top board, you guys have a meter stick. That meter stick is x. It's stationary relative to you. However, on the bottom board, according to me, your meter stick is moving. So then therefore, I see your meter stick as length contracted. I see the meter stick as r. So r is the length contraction of x. So now what I do is the following. I take this expression here for r, and I plug it into here. Like so. And then over here on the right-hand side of the expression, we take the expression for x prime that we found earlier. And we plug it in like so. And then we still have here this plus ut prime. So what I did in this expression here was I substituted in for r, this length contraction expression like so, and then the x prime expression from earlier, I substituted that into here. And then you end up with this really messy looking expression here. And then what we do is we take this expression and we solve it for t prime. When we do, we end up with the following expression. And the expression itself is, by the way, a little weird looking, so I never remember it off the top of my head here. You have the following. This expression here, as strange as it looks. Okay, here's how this expression works if u is small, as it is in the everyday world. So if u is small compared to the speed of light, this term here is equal to 0. If u is small compared to the speed of light, this term here is equal to 0. And then therefore, everybody experiences the same amounts of time in the classical world. Once again, however, the classical world is an approximation of what really happens. What really happens are these expressions here. So these guys right here are the special relativity equivalent of r equals r prime plus ut. And then what we did in the first semester was we then took that position equation and we differentiated it with respect to time. When we did, we ended up with the velocity transform equation, which was v equals v prime plus u. So now we want to come up with the special relativity equivalent of doing so. Okay, to do so, by the way, is easy. The hard part is over. The hard part is actually getting those expressions there, and then therefore I don't even need these diagrams anymore at this point. Okay, so now here's how we come up with the velocity transform. Here's basically what we're interested in finding. The object itself has a velocity in the x direction. It has a velocity in the x direction, v sub x, as measured by the stationary reference frame O. It has a velocity in the x direction, v sub x prime, as measured by the moving reference frame O prime. What we want to do is mathematically relate these two guys to each other. In order to do so, we just have to do a little bit of division. So for example, with the top expression here, the velocity of the object in the x direction according to the stationary reference frame. Just think of this very simply as distance divided by time. Same thing here for the velocity of the object in the x direction with respect to the moving reference frame. Just think of this right here, very simply, as distance divided by time. And now to relate these two expressions to each other, what I'm going to do is take the previously derived expressions over there, still on the far right-hand board, and then plug them into here. When I do, I'll be able to come up with what is called a velocity transformation. So let's go ahead and take those messy expressions over there and then plug them in over here. So first of all, in the numerator of the expression, we have the expression for x prime, which is this. And then we have the expression for t prime down below, which is this. Like so. And immediately this expression starts to simplify. So notice that the radical signs cancel out. So let's go ahead and get rid of that. Okay, let me now write down what I have here at this point. Like so. And now to relate this expression here to this one here earlier, what I'm going to do is mathematically take this expression and multiply it by 1. But I'm going to specifically multiply it by 1 in the following way. I'm going to multiply it by this, and then watch what happens when I do. Okay, so I now have Vx prime. That's going to equal now the following. Let me go ahead and get my sticks here, one of which I need to point with. So I first of all have here x over t, like so. And then minus ut over t, where the t's cancel out. And then divided by t over t, which is 1, and then minus, right here, x over t, and then times u over c squared. Like so. And then right here and here, from the top board, is v sub x. So then therefore the velocity transformation equation is the following. This expression here. So this expression here is the special relativity equivalent of the old v equals v prime plus u. Notice how this expression works here if u is small compared to the speed of light. If u is small compared to the speed of light, this term down here is effectively equal to 0, and then therefore v equals v prime plus u. That's the old style Galilean relativity expression, which is once again an approximation of what really happens. What really happens is this expression here. Now when it comes to actual examples, the only equation that we have to worry about in terms of how we use it is the velocity transformation equation. Using this expression is easy to do, however. Hardest thing, however, is just to identify everything correctly. So we're not going to do any examples involving these position equations, if you will, here for the Lorentz transformation. We're only going to look at the velocity transform. That's only important for our purposes here. Okay, go ahead and access right now today's lecture example, and then go ahead and copy it into your notes. Today's lecture example is what I referenced earlier at the beginning of this process involving these two starships. Okay, while you're copying that problem down, let me go ahead and erase the board one. Okay, now when you use the Lorentz transformation, it's specifically derived by assuming that the moving reference frame is in the positive x direction, by definition. That's how I derived that expression. So then therefore, let's say that I draw out the problem in the following way. So let's say right here's the Earth. Okay, and then here's my first starship like so. I'm going to call this starship number 1 here. And that's moving in this direction relative to the Earth at 90% the speed of light. Okay, and then right here is starship number 2, like so. Moving in the opposite direction like so. Its speed relative to the Earth is 80% the speed of light. Okay, if I draw the diagram like this, what I am specifically saying by definition is that the moving reference frame is starship number 1, because that's moving along the positive x direction. and then therefore the object is Starship number 2. So if I draw the diagram like that, I'm basically asking the following question. What is the velocity of number 2 with respect to number 1? So then therefore, how you define things in the problem, that then determines what the answer is going to look like. Okay, now the two speeds here that I'm given, let me now go ahead and write them as the correct velocity terms in the Lorentz transformation equation. Okay, so Starship number 1 here is the moving reference frame as I've indicated. This right here is O prime, and then Starship number 2 is the object. So then this velocity right here, this is the velocity of O prime, Starship number 1 with respect to the Earth. The Earth, of course, is our stationary reference frame. So this right here is the value of U. And then this right here is describing the speed of the object, Starship number 2, with respect to the stationary reference frame, the Earth. If I give this guy here a negative sign because it points off into the left-hand side or the left direction, this then means that what I'm describing here is the velocity of the object, Starship number 2, with respect to the stationary reference frame. Hence the negative sign because it's pointing to the left. Okay, now that I have everything identified, all that we do at this point is just plug everything into the expression. And this will then give us the velocity of Starship number 2 with respect to Starship number 1. Okay, so here is my expression. Let me just go ahead and plug everything in. Simple as that. Okay, so V sub x is negative 0.8c. Okay, minus then u, 0.9c. And then before I get to the denominator here, notice what the numerator is equal to. It's equal to negative 1.7 times the speed of light, which is what the answer would be in the old Galilean transformation. So if you were sitting here on Starship number 1 and looking at Starship number 2, you would see it moving into the left-hand direction at 1.7 times the speed of light. Okay, we know, of course, that's now incorrect. The denominator essentially corrects for it. Just watch your negative signs when we plug everything in. So in the denominator, I have 1 minus V sub x times u divided by c squared. And then notice that here in the denominator, all of the c's cancel out, like so. And then this negative sign here is going to cancel with this negative sign here to give me a positive, like so. So then in the numerator of the expression, I'm still going to have here negative 1.7c, but then divided by the numbers here in the denominator. So let me go ahead and calculate this out for us. So negative 1.7, and then divided by parentheses here, 1 plus 0.8 times 0.9. So after all of that, it ends up being about 0.988c. So if you were standing on Starship number 1 and you were looking at Starship number 2, you would see it moving away from you in a left-hand direction at 98.8% the speed of light, still below the speed of light. Okay, that's all that's necessary for our purposes here with respect to the Lorentz transformation. Today's shirt was Krisha.